in this video, before we sort of start, work on this warm-up. All right. Hopefully you paused it. I'm going to go over the answer. So for the determinant of 2, 8, 3, 11, just do 2 times 11 minus 8 times 3, 22 minus 24 for a determinant of -2. Once we have that, one over our determinant of -2, swap the middle entries and make the other entries negative. So I could leave it like this, or I could bring the -1/2 inside. So -11 halves, +4, -1, and +3 halves would be our inverse. All right. So sort of remember last time, we want, so given a matrix A, B, C, D, remember our goal at the end of the lecture video last time was we want to find V and W. So A of V equals lambda times V, and W times A is lambda times W. So we care about these sort of types of things. And we're doing this because it's going to help us solve the differential equation. Okay, before we do that, we're going to focus on a very particular case of the above property. So a 2x2 matrix A is singular if there exists some vector V, so A times V equals the 0 vector. Equivalently, another way of saying it is there exists some vector W, say Wx, with W times A equals also all zeros. All right, let's look at some examples to get an idea for what these things sort of look like. So note this is an example of sort of this above property where really lambda equals 0. So, right, because if I multiply 0 by any vector, I'm just going to get the vector of all zeros. Doesn't matter sort of what type. Okay. So, for instance, 3, -3, 1, -1 is singular since 3, -3, 1, -1 times the vector 1, 1, I get 3 times 1 plus -3 times 1, and 1 times 1 plus -1 times 1. And so I get 3 minus 3, 0, 1 minus 1, also 0. So because I plugged in a non-zero matrix, I got out sort of a but I got out, no, all zeros. That means it's singular. I want to note just, from the other perspective, if I multiply by 1, -3, the same thing's going to happen. So 1 times 3 plus -3 times 1. Oops, that's just the first entry, can't end it yet. And then 1 times -3 plus -3 times -1. So here I'm going to have 3 minus 3. And here I'm going to have -3 plus 3, also 0. So again, plugged in something non-zero, got out all zeros. So 12, -2, 8, -3 is singular because 12, 8, -3, -2 times 2, -3. See, 2 times 12, 24, minus 8 times 3, also 24, -3 times 2, -6, plus -2 times -3, +6. So I get, yep, 0, 0. So to see it singular, you only need to satisfy sort of one of these conditions. And it turns out, if it satisfies one, it's going to satisfy the other. So that's enough to show that it's singular. On the other hand, a little bit harder to show, but if I look at this matrix, it's not singular. And to see this, what we're going to do is plug in a vector, set it equal to 0, 0, and then we should see that the only way to get this is if A and B are both 0. So let's see that. So we do the matrix multiplication. We have 1 times A minus 2 times B, and -1 times A plus 3 times B. So this says A minus 2B equals 0, and -A plus 3B equals 0. So if I move this one over, I get A equals 2B. I can plug that in, -2B plus 3B equals 0. Well, that just says B equals 0. But if B is 0, well, A is 2 times B, so A is 2 times 0, so also 0. Okay, so a little bit harder to show that something's not singular, at least sort of directly. We'll see soon in a bit. There's a shortcut. But this is sort of the idea. I'm going to do one more example just to make a point. So 1, 2, 0, 0 is singular. And here I note that, in the definition, actually I forgot to write this. So in the definition, you can always use a zero vector, but the definition requires that v is not the zero vector. Sorry, missed that. Okay, so even though you can still have one entry to be equal to 0, like in this case, 1 times 0 plus 0 times 1, and 2 times 0 plus 0 times 1. So yeah, so as long as there's some vector, not all of the entries are 0, and you can multiply it and get 0, that means it's singular. All right. So we're going to see a real important property of the determinant. That is a matrix A, B, C, D is singular precisely when the determinant is 0. Okay. So this is going to be sort of the key thing, and because it's sort of so important, I just want to give some sort of reasoning why. Okay, so let's look. A, B, C, D. So the idea is sort of, I want to multiply by something that's going to guarantee that sort of at least, let's say this entry is 0. So what can I multiply by so that this entry is 0? So this is going to be xy, right? I want cx plus dy to be 0. Okay. Well, one thing I could do that's kind of obvious if you think about it is I could make x equal to d. So the first entry is d, and my second entry is negative c. So I just sort of swap c and d, and I add a minus sign to 1. So let's see what we get. So in the first entry, we have a times d plus b times negative c. And in the bottom entry, we have c times d plus d times negative c. So here we have AD minus BC and CD minus CD. So here I can see AD minus BC. Oh, that is just the determinant. And down here I get 0. So if my determinant is 0, well, I have found my vector that if I plug in, I'm going to get 0. If it's not 0, then it turns out that sort of as soon as I make one entry 0, the other entry essentially has to be the determinant or like something times the determinant. And sort of similarly, the reason why it doesn't really matter, if I do, let's say, C minus A over ACBD, I'm going to have CA plus negative AC for the first entry, and the second entry, CB plus negative AD. So I have 0, and then here I'm actually going to get not the determinant, but negative the determinant of A. And so this sort of happens in general. If I try to go ahead and make one entry 0, then the other entry is a multiple of the determinant. And so that's sort of why it's related to this property of being singular. Okay. So on to sort of the main point. So given a matrix A, B, C, D, we say lambda is an, we have a weird word here, eigenvalue of A if there is some vector B. So A times V is equal to lambda times V. And I should say sort of equivalently, I could do this the other way. So I'll do W, some W. So W times X times A is lambda times W times X. So it's the same thing. If there's some vector like this where this happens, there's always got to be some opposite vector, like where some row vector, some longer vector where that happens as well. Okay, so that's one piece, an eigenvalue. If A times V equals lambda times V, then we say V is an eigenvector of A with eigenvalue lambda. All right. So again, let's look at some examples. So for instance, if we have 2, -5 and 1, -4, and we multiply by 1, 1, we get 2 minus 5 and 1 minus 4. That is equal to 3, 3, which is 3 times the vector we started with. So 2, -5, 1, -4 has 3 as an eigenvalue. Stated differently, 1, 1 is an eigenvalue or an eigenvector of the matrix 2, -5, 1, -4 with eigenvalue 3. let's say on the other hand, I multiply by something like 3, 1. Right, so that's going to be 2 times 3 minus 5 times 1, and 1 times 3 minus 4 times 1. So 6 minus 5, that's 1, and 3 minus 4 is negative 1. So what this tells us is, right, I went from 3, and now we can ask, is there some value I can multiply by to make this true? Well, if I look at the system, it says 3 times lambda is 1, and lambda equals negative 1. This has no solution. Pretty clearly, if lambda is negative 1, 3 lambda is negative 3, not 1. No solution. So what this tells us is 3, 1 is not an eigenvector of 2, negative 5, 1, negative 4. Okay. So most vectors you plug into a matrix, apart from like very, very specific matrices, you will not get an eigenvalue, or will not be eigenvectors. If you just sort of picked a vector at random and you multiply it by a random matrix, it's not going to be an eigenvector for that matrix. Okay, so one thing to note, 0 is an eigenvalue of our matrix A precisely when the determinant of A is equal to 0. And again, sort of the question is why? Well, if A times some vector V equals 0 times some vector V for some non-zero vector, right, then A is singular. And as we sort of just discussed before, if A is singular, its determinant is 0. All right. So enough sort of setup. Let's just go through how exactly do we find eigenvalues. So let's do an example. We'll find all eigenvalues and eigenvectors for 8, negative 2, 10, negative 1. Okay, so here's how we're going to sort of proceed. So, right, we want to find sort of lambda A and B. So 8, negative 2, 10, negative 1 times AB equals lambda times AB. And, we want to find these sort of as long as A and B aren't both 0. Because if A and B are both 0, well, that's going to be true for every single lambda. So what we're going to do is kind of do a trick. So we're gonna represent, right? So this is lambda times AB is just lambda A, lambda B. Okay, well there's another way I could write that. If I look at the matrix where I have sort of zeros here, but on the main diagonal I have lambdas. I multiply that by AB. Right, I get lambda A plus 0 and 0 plus lambda B. So I get lambda A, lambda B. So I can write this right-hand side like this. Okay. Well, now I sort of have, right, like this shared term, so I can move everything over to the other side. Let's do that. So negative 2, 10, negative 1. And now I can sort of pull out the AB. And I see that I get the following. Oh, no, not 0, but negative 2. Right, so I remember subtraction is just entry-wise, so 8 minus lambda, negative 2 minus 0, 10 minus 0, and negative 1 minus lambda. So what we see is that if AB is an eigenvector, of our starting matrix, 8, negative 2, 10, negative 1, with eigenvalue lambda, then 8 minus lambda, negative 2, 10, negative 1 minus lambda times AB is the 0 matrix, right? Didn't say that, but those zeros on that side, that's the 0, or not the 0 matrix, but the 0 vector. So what this says is this matrix is singular. So the determinant is equal to 0. So now let's go ahead and compute that determinant. So 8 minus lambda, negative 1 minus lambda, minus negative 2 times 10. Let's see, and then here we're going to get 8, or negative 8, and then plus lambda minus 8 lambda, so minus 7 lambda plus lambda squared, and then minus negative 20, so plus 20. Negative 8 plus 20 is 12. Okay, so we got that, and now up here we realized we want to know when this is equal to 0. So it be lambda squared. Well, we can factor it pretty easily. Lambda minus 3 and lambda minus 4. All right. So because sort of these are when the matrix is singular, these these have got to be our eigenvalues. I mean, at the very least, they're potential eigenvalues because of sort of what we said before, but let's just confirm that they actually are. So we found the eigenvalues, and now we're going to find the eigenvectors. So, we could do this two different ways. We could either try to solve this equation, 8, -2, for instance, for 3, 10, -1 times AB equals 3A, 3B. Or we could just sort of stick with this thing here. So 8 minus 3, -2, 10, -1 minus 3, AB equals 0, 0. So for this step, you can actually solve sort of either one of these. In my experience, this one tends to be a little bit faster, so that's the one I'm gonna work with. So 8 minus 3 is 5, -2, 10, and -1 minus 3 is -4. Okay, so we do that, and we want this to be equal to 0, 0. So we'll just expand this 5a minus 2b and 10a minus 4b. So 5a minus 2b equals 0, and 10a minus 4b equals 0. So 5a equals 2b, and 5a equals 2b. So again, when we're finding these eigenvectors, we want this to be redundant. We want both equations to sort of cancel out. And so usually what we do is we only sort of really care about one eigenvector, but that's not always the case. So we can see that 2, 5 is an eigenvector. And more often, if we're asked to find sort of all eigenvectors, we can just sort of take one of these and be, okay, 5a over 2 equals b. And so I could represent all eigenvectors as a 5 halves a. However, this is sort of the thing, right? If a is just an arbitrary constant, I kind of want everything to be as nice as possible. So usually what I would say is all the eigenvectors, are some constant c times multiply top and bottom by 2 times 2, 5. So all eigenvectors are of that form. That was just the eigenvectors for 3, but let's do it for the other one. So 8 minus 4 right, our other eigenvalue is 4, so we're going to use this again, 8 minus 4, -2, 10, and -1 minus 4. Well, that is 4, -2, 10, -5. And so now we set up this equation for -2, 10, -5, AB. Want it to be the 0 vector. So this says 4a minus 2b equals 0, and 10a minus 5b equals 0. If I move the b's over and divide, I get 2a equals b and 2a equals b. So again, got the same equation if I fully reduced. That's exactly what I want. And all eigenvectors are now of the form A times 1, 2. Okay. So let's do a different, okay, I guess before that, so how do we sort of, let's summarize a little bit what we just did. So to find eigenvalues of A, B, C, D, we look for lambda, which makes the determinant of this equal to 0. So this, if we fully expand it, A minus lambda, D minus lambda, minus BC, this is what's known as the characteristic polynomial of our matrix A, B, C, D. And what we just sort of saw is the roots of our characteristic polynomial are the eigenvalues. All right, do one more example before leaving you guys on an exercise. So find the eigenvalues of 5, -4, -6, 10, and for each one, find an eigenvector. So what we do first is we look at our characteristic equation, our characteristic polynomial rather, and that is the determinant of our matrix where we have minus lambda on the diagonal. All right, so we should get lambda squared minus 15 lambda plus 26. So this is our characteristic polynomial. We now want to set this equal to 0. This one, with a little bit of work, we can factor lambda minus 2 and lambda minus 13. So now we have our eigenvalues of 2 and 13. Okay, we look at our eigenvalue of 2, and let's set this up. So 5 minus 2, -4, -6, 10 minus 2 times AB. Want that to be equal to the 0 vector. So what we should end up with is -8a minus 4b equals 0 and -6a no, sorry. 5 minus 2, I'm sorry, I am jumping way ahead. 3a minus 4b equals 0, and negative 6a plus 8b equals 0. And now we can see that, one eigenvector at least is going to be given by 4, 3. Now if we do lambda equals 13, we should have 5 minus 3, negative 8a minus 4b, and negative 6a minus 3b. And so we should be able to get our other eigenvalue of 1, negative 2. Now again, these things are non-unique, so I can always multiply by a scalar. So for instance, negative 1, 2, another eigenvector, negative 2, 4, another eigenvector, and so on. So there's infinitely many. I can always just multiply by a scalar, but that is what we need. Okay, so now to just end it, I'm just going to give you guys an exercise. So for the first one, we're going to have 7, negative 3, 5, negative 1. And for the second one, we'll have 10, negative 4, 9, negative 2. Okay, so go ahead and try these. Okay, now the answers. So for your characteristic polynomial, for this one, you should have gotten lambda squared minus 6 lambda plus 8. And so you're going to have eigenvalues of lambda equals 2 with eigenvectors of the form, let's say C1 times 3, 5. And for your other eigenvalue, it's 4 with C2 1, 1. For your characteristic polynomial down here, you're going to get lambda squared minus 8 lambda plus 16. So this case is a little weird. You only have one eigenvalue, lambda equals 4, and the eigenvectors are just some constant c times 2, 3. So this last case is sort of interesting. You don't always have to have 2 eigenvalues, though most of the time you will. Right, I'm going to end it